The nominal response model is an item response theory model, which is used for modeling the responses to a test or questionnaire. In this when we have polytomous responses for each question. In this model, the probability of giving a certain response to one question depends on a latent variable. That is denoted here by theta I. I is the index of the subject. And the parameters, so key is the question and J is the item. And the parameters of the model are these beta parameters, beta and alpha. Beta are the intercepts, and we have one different intercept for each item and each response category. And then we have these low parameters, alpha, which are take again a different value for each item and each response category. So we had a lot of parameters in this model. And this figure shows the probability curves, which are the probabilities of giving for one item for these 4 response options at different levels of the latent variable. In order to assure the identifiability of the parameters, it is necessary to impose some constraints. And in my work, I assume that one slope parameter and one intercept parameter of one category for each item are set to 0. This is a very flexible model, certainly the most flexible item response theory model for polytomous responses. However, it involves the estimation of many parameters, because for each item, we have a couple of parameters for each response category, with the exception of one. These parameters are usually estimated with the marginal maximum likelihood method, and then assuming a standard normal distribution for the latent variable, and then integrating it out. However, the maximum likelihood estimates can be very variable and also biased, especially in small samples. So the idea of this work is to regularize these estimates. The lasso is a very popular regularization method which was first proposed for the regression model. And it has the effect of shrinking the coefficient towards 0 and setting some of them exactly at 0. And it requires the minimization of a loss function that for the linear regression model is the residual sum of squares, plus a penalty term where we have the sum of the coefficients in absolute value multiplied by this tuning parameter lambda, which determines the amount of shrinkage. So the idea is to use the lasso type penalty for the nominal response model. In the nominal response model, however, when 2 slope parameters of 2 different response categories of the same item are equal, these 2 can be collapsed. They can be considered together, thus saving a couple of parameters. So the proposal is to use a penalty that encourages the slope parameters of the same item to assume the same value. So I consider the differences between slope parameters of the same item. So this is similar to a fused lasso penalty. However, here there is not a natural order between these coefficients. So I consider all the response options, all possible couples of response options. And since one of these coefficients is set to 0 for identifiability, this penalty has the effect of shrinking all of them towards 0. So for large values of lambda, all these coefficients will be all equal to 0. Okay? But let's see how this penalty works in practice. So on the left, we have the probability curves that are obtained with the maximum likelihood estimates that we have when the tuning parameter is equal to 0. And on the right, we have the estimates of the parameters at different levels of lambda. The continuous lines are the slope parameters, the dashed lines are the intercepts. So if we increase the value of lambda, these slopes are shrunk towards 0, so the curves become more flat, and at a certain point, these 2 parameters are fused. So at this point, these 2 curves overlap, and this means that at this value of lambda, these two response categories can be collapsed. Okay? If we go on increasing the value of lambda, these curves become more flat, and at the third part, they are completely flat, because here, these low parameters are all equal to 0. And this means that there is no more relation between the latent variable and the probability of giving a certain response. I explored also an adaptive version of this penalty that includes these weights that depend on the maximum likelihood estimates. So when the maximum likelihood estimates of these low parameters are very close, this weight is very high, and then it is very likely that these low parameters are fused. The maximization of the likelihood function is not very simple because the absolute value is not differentiable. I explored various algorithms already proposed in the literature to handle this kind of problem. And the one that worked better, at least for this case, is the approximation of the absolute value with a differentiable function, which is given by these expressions, with a quadratic function, where C is a very, very small value. And then, after approximating the absolute value with this quadratic function, you can just maximize the log likelihood using standard optimization routines. The tuning parameter lambda was selected using cross-validation, and I implemented in R and C++ all these analyses. Okay? I applied this procedure to to a real data example, considering these TIMSS data. TIMSS is a large-scale international study which monitors the achievement levels in mathematics and science in many different countries. And in this example, I consider year 2011 the subject of mathematics and students at the 8th grade. I consider in this study there are many items. I consider just one block of items because these were all released. Other items are not released. And these include 5 multiple choice items. So one item with 4 or 5 possible response options, and just one is correct. And 6 constructive response questions, which are questions that are answered by the student without having predetermined responses. And we have, for the multiple choice items, I consider the response is just correct or not. Instead, for the constructive response questions, we have many kinds of responses, and I'm going to show you an example of a constructive response questions shortly. So for this data set, we have 52 parameters, so a large number of parameters. And selecting only students from the United States, we have almost 700 students. Okay, this is a constructive response question, and these are the scoring guides of a constructive response question. So we have 2 different codes for a correct response. These 2 responses correspond to a correct response. These other kind of responses are considered a partially correct response, and these kind of responses are considered an incorrect response. And I consider all these different codes as different response options in order to see if the procedure indicates that these 2 codes can be considered together as just a correct response, as well as these other 2 codes. Okay. And these are the estimates of the parameters at different values of lambda. So we can see that these are the slopes of the 2 correct responses, and we see that they are fused together using the non-adaptive penalty and also using the adaptive penalty. Okay? Also, the 2 partially correct responses are fused together, while the 2 incorrect responses are not. However, at the selected value of lambda, using the non-adaptive penalty, none of these categories is fused. Instead, using the adaptive penalty, the two correct and the two partially correct responses are fused. So the adaptive penalty seems more effective in collapsing the responses. I also ran a simulation study in order to see the performance of this procedure. Here we have 4 items, each with 4 response categories. And these are the probability curves. And for this item, for the first item, 2 slope parameters are equal. So in fact, the 2 curves overlap. And I did this on purpose in order to see if the procedure indicates that these 2 response categories can be collapsed. Okay, I assumed I took different sample sizes and 500 replications. Okay, in this table we found there are the number of cases out of out of 500 in which these 2 slope parameters are fused at the selected value of lambda. So using the non-adaptive penalty, not much cases they are fused. Instead, using the adaptive penalty, the number of cases in which the 2 slopes are fused is much higher, and it increases with the sample size. So the adaptive penalty is more effective in collapsing the response categories. In these figures, there is the bias in absolute value of the estimates. And we can see that the maximum likelihood estimates can be very biased in small samples. In a sample size of 200, the bias can be really high. And the penalized estimates present a much smaller bias. Okay, there is not much difference when the sample size increases, and for large sample, maximum likelihood performs a bit better, but the values here are all small. Okay, this was the non-adaptive penalty. Instead, using the adaptive penalty, the results are very similar, and in particular, for a large sample, the bias is almost the same as the maximum likelihood. None of the methods matter. Okay, in these other figures, we have the root mean square error, and we can see that we have large gain in efficiency for a small sample. And for a large sample, there is no difference between the penalized estimates and the maximum likelihood. And the results for the adaptive penalty are very similar in terms of mean square error. This method is implemented in the NAR package that is available on GitHub. The package is RegIRT, which is for regularized item response theory. Currently, in this package, there is only this procedure, the regularization of the nominal response model using this penalty. But I'm planning to include in this package other regularization methods for item response theory models. And the main function is this function nominal mode, and which takes as arguments the data, the number of dimensions, which are the number of latent variables. In this case, it's just 1. But I'm working on the extension to more than 1 latent variables. The initial parameters, the values of the tuning parameters, which can be just one of a vector of values, the type of penalty, in this case, a lasso penalty, and whether the penalty is adaptive or not. If the penalty is adaptive, then we have to specify also a vector of parameter to be used as weights, which are the maximum likelihood estimates. Then in the package, there is a function that performs cross-validation and the function that plots the regularization path, which are those figures that show the estimates at different values of lambda. So concluding, the proposal is effective in collapsing the response categories, especially using the adaptive version of the penalty. It provides regularized estimates, not only of the slopes, even if the penalty involves only the slopes, also the intercepts are regularized. If we go back to these figures, we can see that the intercepts, here is not very apparent, that the dashed lines tend towards 0 as well. And it reduces the bias and improves efficiency, especially in small samples. So, and currently working on the extension to the multidimensional case of this model. Okay, these are a few references, and thank you very much for your attention.
Thank you very much, also for being kind. Okay, questions?
Very nice talk, very clear, and I like the penalized formulation. About the adaptive weighting, it was nice that you studied how the coefficients fuse better than the unadaptive version and how you studied the bias. But I was wondering if you studied the prediction error or the prediction accuracy in cross-validation experiments of the adaptive strategy or the non-adaptive strategy.
No, I did not. Actually, here is hard to predict because you don't have a continuous response. Yeah, you can try to predict which is the response that could be the one with that has the maximum probability at that level of the latent variable. As I did not try, in fact, as cross-validation error, I did not consider the prediction, just the value of the log likelihood function evaluated with the parameters estimated in the training set. Yeah.
Okay, thank you very much.
Yeah.
Thank you.